We usually imagine electricity as a solitary traveler, a stream of invisible electrons rushing through copper wires to power our homes and cities. But these electrons never travel alone. Whenever an electric current flows, it generates an invisible, swirling magnetic field that wraps around the wire. In the early 19th century, scientists realized these forces were linked when a nearby compass needle deflected every time a circuit was closed. This relationship follows a predictable geometry. If you point your right thumb in the direction of the current, your fingers will naturally curl in the direction of the magnetic field, forming a circular path perpendicular to the flow. This means we are surrounded by an invisible architecture of magnetic cylinders, layered around every live wire hidden in our walls. While the magnetic field from a single wire is weak, we can multiply its strength by winding that wire into a dense coil, or solenoid. Wrapping these coils around a metal bar concentrates the magnetic flux, creating an electromagnet capable of reacting to other magnetic fields with immense force. This cross-section demonstrates how we harness this interaction. A current-carrying wire loop between stationary magnetic poles causes the field lines to bend and distort. This creates a physical push and pull. Side A is thrust downwards and side B upwards, forcing the loop to turn. This continuous rotational action provides the foundational principle behind every electric motor in existence. By using electricity to create magnetism, we learn to translate raw energy into the physical, mechanical motion that drives our world. If moving electrons create a magnetic field, what happens if we do the opposite? What if we move a magnetic field near stationary electrons? In the 1830s, Michael Faraday explored this inverse relationship, seeking to generate electrical power using magnets alone. He discovered that moving a magnetic field in and out of a coil transfers energy. This process, induction, forces electrons to move, building measurable voltage. A stationary magnet does nothing. The faster the magnetic field moves, the higher the voltage produced. Faraday proved that moving a magnetic field creates the potential to do work, meaning we can turn mechanical force back into electrical energy. Scaling this principle up created the modern power plant. We spin a massive electromagnet, the rotor, inside an outer ring of wire coils called a stator. We use kinetic energy, steam, wind, or falling water, as a prime mover to physically force these giant rotors to spin against magnetic resistance. Because the spinning motion continuously changes the alignment of the magnetic fields, the induced voltage pushes and pulls in waves, creating alternating current. These massive belt-driven generators allowed us to produce the grid-scale power that defines modern life. Induction serves as the ultimate energy converter, allowing us to harvest raw mechanical motion and transmit it instantly as electricity. If electricity makes magnetism, and moving magnetism makes electricity, we can layer these effects to create the transformer. A transformer consists of two separate coils of wire wrapped around a single iron core. Crucially, the two coils are physically isolated from each other. When we feed alternating current into the first coil, it creates a dynamically shifting magnetic field that travels through the iron core. As this changing field passes through the second coil, it induces a brand new electrical voltage, allowing power to jump across the gap without a physical connection. This transformer action allows us to alter voltage levels at will. It is the invisible bridge that makes the global electrical grid possible. Electricity and magnetism are two perspectives of the exact same fundamental force. They exist in an elegant, perfect symmetry. Physical motion generates electrical power, and electrical power generates physical motion. Every machine we use and every light we turn on depends on this constant, reciprocal relationship. Our civilization functions because of this invisible, perfect symmetry of electromagnetism.